Hello and welcome. In this three-part video series, I'm going to be covering some of the basic curves in just two dimensions. And I'm doing that at this point because we're going to need these for three-dimensional surfaces and quadratic surfaces, which we're getting into in section 13.6. So what we're going to need for section 13.6 for these quadratic surfaces are, well, we're going to need to be able to recognize certain two-dimensional curves as sort of slices, cross-sections, or what we'll call traces of three-dimensional surfaces. So we're going to need to recognize equations for these three basic curves in two dimensions: parabolas, ellipses, and hyperbolas. So in this first video of the series, I'll just talk about parabolas. And most likely you're quite familiar with parabolas. We've talked about these in Calc 1 and Calc 2. You've seen them before in like a algebra class or a pre-calculus class. I'll start with a form you will probably recognize. So I'm going to just let a be a real number here. A is just any real number, and I'll let y equal ax squared. So this is a nice form for a parabola. Again, you might recognize that this is, and this is a parabola that's centered at the origin. So centered at origin. So this just covers parabolas that are centered at the origin and which have a certain orientation. So this one is centered at the origin. And let's just, I just want to investigate the form of this expression, of this equation, just to see what the properties of it are. Okay. So I'm going to be looking at just y equals ax squared. And I'll put my y-axis here and my x-axis here. So when I'm graphing something like this, it's important to note what are the intercepts. And maybe you're familiar enough to know that this is centered at the origin. Its vertex is at the origin. What's another way we can recover that if we don't recognize this form? Well, one thing I can do is I can set x equal to 0. So the line x equals 0 is the same as the y-axis, right? At every point on the y-axis, x is equal to 0. And so what I'm doing by setting x equal to 0, I am finding all the points on this curve for which x is equal to 0. So all the points on the curve that intersect the y-axis. And so if I do this, I get y equal 0. Right? If I substitute 0 for x, I get y equals 0. So that tells me there's one intersection with the y-axis, and it occurs right here at the origin, 0, 0. So that's the only point that intersects the y-axis. I can set y equal to 0, and I'll recover that x needs to be equal to 0, telling me the only place this parabola intersects the x-axis is at y equals 0. So that gives me just two intersection points which happen to be the same. Another thing I'll note here is what if I set x equal to 1? So I'll set that and just see what y values correspond to an x equal to 1. In this case, I get y equal to just a. And so here, if let's maybe put 1 right here, 1 on the x-axis. I'm going to do -1 as well. I'll put that over here. Set x equal to 1, y is equal to a. So up here, somewhere, whatever my a value is where 1a will be a point on the curve. Oh, maybe I'll use blue for that. I'm using blue for the curve. White for all the other bits. And notice the symmetry in this equation. If x is negative, it's the same as if x is positive for the same absolute value. So also setting x equal to -1 should yield the same result. I get y equal to a. And so -1 and a again. And then we just happen to know, I mean, we could graph more points, but we happen to know that this is the form of a parabola. We can recognize that much at least. And so I can sort of just eyeball the rest of the curve, right? Oops. Right, I can eyeball the rest of the curve here. It goes up like this, and it opens upward. And from this sort of, and it keeps going. For this sort of investigation here, setting different x values, I can also sort of think about, well, what if my a were negative? So here I've drawn a as positive, positive values of a. If a were negative, then our parabola would be opening downward, as I'm sure you're familiar with, right? So opening upward, opening downward. Now, what if instead of y equals ax squared, what if we did something like x equal a y squared? So what about something like that? What if we did x equals a y squared? Well, then my analysis is very much the same, but with x and y switched. So again, if I plug 0 in for, say, y, I'll get a 0 for x. I know that the origin, again, is on this curve. But now, here's my x again, here's my y again. Now if I say set y equal to 1, so what points on this curve intersect the line y equals 1? Let me put y equal 1. Oh, how about right here? 1. And down here, -1. If I set y equal to 1 or y equal to -1, so set y equal to, I'll say plus or minus 1, then x is equal to plus or minus a. So if y is equal to 1, then x is equal to a. Let's say it's somewhere up here. And I get the point a1 rather than 1a, which I got before. And so what we're getting now is a parabola that instead of opening upwards or downwards, opens left or right. That was a really bad drawing. Let me try that curve once again. It's got this parabolic shape. Goes off like that. And another sort of parabolic shape. All right, my drawing's not great. The idea is to keep in mind these things. By graphing these points y equal plus or minus 1, plus or minus a, and just knowing the underlying structure of what a parabola looks like, we can sort of recover the curve of it. Again, if a is negative, my parabola would be pointing this way, so to the left rather than to the right. So this would be for a less than 0, and over here would be for a greater than 0. So up, down, left, right, depending how I change this. Let me throw another equation at you that has this form. What if it was something like, oh, how about z equals a y squared? So if I have z equal a y squared, I do want to think of this like I've thought of the other ones, like my independent variable here is z, and my dependent variable is y. So what I'm going to do is I'm going to let this be the y-axis and this be the z-axis. And now this has the form of like the y equals ax squared business, which we saw before. And so my parabola is going to look something like this if a is positive, or something like this if a is negative. And again, I can find these points on the line by setting, say, y equal to 1 or y equal to -1 and recovering what z should be, right? This will be the point 1a, just like the other ones. So the point here I'm trying to get with this third example of the parabola is that it doesn't matter what my variables are, as long as I can locate those axes. Graphing it is much the same as just graphing y equals ax squared if we just sort of transplant the variables given our axis situation. So this is sort of the idea of parabolas. I think I'm going to leave it here. These are the more easy to work with ones. Again, drawings aren't great. That's okay. We just want to be able to recognize this form of the parabola when we see it. All right, that's it for this one. In the next video, I'm going to talk about ellipses.